So I will be telling you about what this tempo algorithm is that we came up with, how this builds on the copy results, which Nancy talked about earlier, and kind of just showing the way that we think about these things, which I guess is slightly different, coming from a more kind of condensed matter physics background, as opposed to a chemical physics and chemistry kind of background, which we heard about earlier. Okay. Yep.
Can't quite hear you so well. Is your microphone working?
Yeah.
Okay.
Okay. Mouth. It in the right direction. It doesn't really flip, but okay.
Thanks.
Is that better? Okay, good. So, yeah. So we really want to talk about developing methods for exactly simulating non-Markovian open quantum systems, and that's exactly the topic of this workshop. So what I wanted to do is just point out the difference that, at least in the way that we think about this, as to what we mean by Markovian and what we mean about non-Markovian open systems. So Markovian systems are described by master equations, and hopefully everybody is familiar with those kind of descriptions. And when you derive the standard Born-Markov master equation, there are a series of assumptions that you make about the nature of the interaction of my system with its environment. You make the assumption that the interaction between these two parts of the universe is weak, so the system and environment are not strongly interacting with each other. There's some distinction I can make between the part of the world that I'm going to call the system and the part of the world that I'm going to call the environment. And also, typically, you make the assumption that the spectral density of the environment is flat. So you have this idea of a time local master equation for the dynamics of your system, where you can just say, okay, I know the density matrix at the current time, I can propagate that thing forward a step into the future, and that then tells me, okay, this is what the density matrix is at the next time point, and I can propagate that thing forward, and I don't need to know about what had happened at previous steps to know what's going to happen in the future. So we have this idea of, to get my density matrix at time t plus dt, I can just apply this time evolution propagator, which takes me from the density matrix at time t. And in the kind of pictorial tensor network kind of language that we're going to use later on, all that is I take my density matrix which has a single index, and then I propagate it forward one time step into the future with this object which has two indices, an incoming and an outgoing, and I get another density matrix back. And later on, we'll talk about this tempo algorithm and how that's a different way of thinking about this, and one which is able to include these kind of history effects, which you don't get in this Born-Markov Markovian description. There are a lot of places where this kind of physics is really important to be able to describe. So a few examples which I've taken from, I guess now, slightly old literature. Things like quantum dots. So if I have some small few level quantum emitter sitting on a solid state environment, then there's typically very strong interaction between the degrees of freedom of the quantum dot and the degrees of freedom of the solid state substrate which it's sitting on. There are also cases where you have arrays of superconducting circuits, so superconducting qubits coupled by microwave transmission lines, where really the fluctuations in the superconducting circuit can affect the behavior of what's going on in the transmission line in a way which isn't well captured by these non-Markovian descriptions. There are also some experiments on optomechanical systems where you really have to start caring about the structure of the environment. So I guess there are two and probably more ways that you can break this idea of having a Markovian system. You can think about cases where the interaction between the system and the bath is strong, but you can also think about cases where the structure of the environment is a thing which you're really going to need to take care of. Okay, and the slides change very slowly. There we go. Okay, so the generic model which we're going to think about for everything that I'm going to talk about today is a generalized spin boson model. So in the language of solid state physics, we have something where I have a system which has some Hamiltonian H0, and then it's coupled to a harmonic bath. So there's some set of harmonic oscillators, possibly an infinite set of harmonic oscillators, which couple to my system, and they couple via some O, some operator which lives in the system Hilbert space, and that couples linearly to the coordinates of the environment, and then there's some frequencies for those harmonic oscillators which give rise to the final term in this Hamiltonian. And really what you need to know about the environment to be able to do calculations with this is just the spectral density function. So this sum over all of the modes of the coupling squared, and the particular form of this function j of omega is the thing which really plugs into all of these methods and gives rise to all of the non-Markovian dynamics. And so this is the thing which you're going to care about with the environment. And we'll talk about different forms of these spectral densities as we go on. So there are a variety of methods for treating these kind of systems, many of which will be talked about by various people over the course of the workshop. The first thing you can think about are exactly solvable models. So the typical example which one thinks about with this is the independent boson model. So where the coupling to the environment commutes with the system Hamiltonian. And in that case, you can go through all of the mathematics analytically and come up with exact solutions for what's going on. And we found actually this independent boson model gives a nice test for anything that you're doing. If you don't get that right, then you're not going to get anything else right beyond that. There are more complicated master equations, so not just the typical Born-Markov master equation, which one can write down. So you can do things like polaron transform the Hamiltonian of the system and environment before you start doing a weak coupling theory. And in that case, you can find parameter regimes where the effective coupling that you come out with after you've done this transformation is weak, and then you can do kind of standard perturbation theory on that to come up with a description for the dynamics of the system in a different basis, which is nicer and simpler to deal with. You can think about increasing the number of equations of motion or the size of the Hilbert space that you're dealing with. So you can say, okay, I have some non-Markovian environment. It has some structure to it. I'm going to bring in the modes associated with that structure into my system degrees of freedom. And in that case, I then have a different boundary between the part of the world which I think of as the system and the part of the world which I think of as being the environment. And this can allow me to do more things, but there I have to really make assumptions about the particular form of the spectral density which I'm going to use. So that's increasing the system space. We can also increase the number of equations of motion. So there are these hierarchical equations of motion or hierarchies of pure states where you couple in different parts of the environment and keep track of a higher number of degrees of freedom than just the density matrix elements for the system, which you want to keep. And then there's recording the history. So ideas like the QAPI, which we heard about already this morning. So you keep track of the history of what the system did in the past and keep track of all of these paths which couple those things. And it's exactly these kind of ideas which we're going to talk about over the next few slides to build up to the tempo algorithm, which we're going to describe in this talk. Okay, so what I wanted to do was just give a kind of pictorial representation of how we think about what's going on in these kind of systems. So we want to describe the dynamics of one particular part of the universe, which we're going to call the system, and we're going to do this by doing this path integral representation of quantum mechanics, and we're going to then integrate out the environment to come up with these influence functionals, which we saw earlier. So this is very similar to the mathematics that we saw in the previous talk, but I'm going to do it with pictures rather than with mathematics. So we have some system which has some coordinates x, and I'm starting it at some time ti, and I want to propagate it to some time tf. And what happens is it takes a variety of different paths between these two between the initial state and the final state. And I can parameterize that by some action which describes all of these different paths. And then if I take the rest of the universe into account as well, and I have no interactions at the moment between the system and the environment. So my environment degrees of freedom are described by this capital X. And again, I have a load more paths which take me from the initial state of the environment to the final state of the environment. And so this is exactly the same as we had for the system. It's just the environment has a lot more degrees of freedom than the system has. In the end, we're going to want to talk about density matrices, so we don't just have evolution forwards in time, we have evolution backwards in time as well, so I get a pair of these things. But at the moment, this is just Hamiltonian evolution of a Hamiltonian for the system and environment, so these forward and backwards parts are exactly the same because it's just evolution under a Hamiltonian. Then if I introduce coupling between the system and environment, that means that what happens in the path for the system can depend on what's happening in the particular path for the environment, and vice versa. And again, that happens forwards in time and backwards in time. But then when I do this Feynman path integral over the environment degrees of freedom, what I get is something where the paths which go forward in time couple to the paths which go backwards in time, and the paths which are going forwards in time can talk to each other at different time points. And this is exactly the origin of this non-Markovian behavior of the system when I trace out the environment, because what I had before was just time local dynamics of a system plus environment. But when I trace out the environment degrees of freedom and I no longer know what they're doing, then I get these non-Markovian interactions between the forwards and backwards evolution of the system. And that's really parameterized by this influence phase, which is the thing which shows up in these influence functionals. So it really depends on integrals over the correlation function, which is just the Fourier transform of the spectral density of the environment that we had before. Okay, so let's write that out in some slightly more formal mathematics. So if I start from some initial density matrix at time t1, which has indices which I'm going to call j1, at the next time step, what I do is I multiply in one of these influence functionals, and that takes me from time step 1 to time step 2. And this is just Markovian evolution, but now I'm going to need to keep what had happened at time step 1 to be able to know what's going to happen at time step 3. So when we do this and we keep propagating forwards in time and forwards in time, then we get this big product over these influence functionals, which take me from time step 1 to time step n. So I have some sum over all of the degrees of freedom, which I want to get rid of to just give me my reduced density matrix of the system at a particular time. But to get these intermediate points, I need to keep all of the kind of history of all of the things that had happened. And these influence functionals are just related to this influence phase, which I had on the previous slide. But if they're kind of the time local one, then they have an extra bit, which is to do with the system Hamiltonian or any Markovian dynamics which are happening to the system on the time scale of the kind of time local time point. So now we have this fairly horrible looking expression for what is the density matrix at time point n, and it has this exponential number of products of influence functionals which move into it. Then we can do this kind of identification of this augmented density tensor, which is exactly what is done in the Quappy algorithm. So you can identify this object, which I'm going to call A, which is just multiply in the set of influence functionals which I need to get me to time point n. And that thing, before we do this sum to get down to just the reduced density matrix, has a set of n legs. So this is a tensor which has indices corresponding to each time point in the history which I propagated forward. And to propagate it forward one step further in time, it grows one leg. So I can think of this as tensor-tensor multiplication, where I take an n-1 index object. I multiply in with another layer of things, which grows me by one time step into the future, and I get an n-index object. And so this propagation can really be written, take the augmented density tensor at time step n-1, multiply in with an object which just contains information from the influence functionals, and take me to time step n. And if I put all of this together, then this really starts to look like tensor-tensor contraction, and it starts to look like something which we can use MPS type techniques onto to try and compress. So I do this multiplication and I end up with an object which has one more leg than the thing that I started with. So this then leads us to this tempo algorithm, which is really an MPS representation of the Quappy algorithm, which we heard about earlier. And we can also do things like this finite memory approximation. So putting all of this stuff together, we start with an input state, which is just the density matrix of my system at t equals 0. We then keep multiplying in and multiplying in these objects which grow this density matrix to have an extra leg, so to have an extra piece of information about one more time step in the past. And I get this kind of tensor network diagram. I can then think about this memory length, finite memory length approximation as saying, okay, when I have grown to have so many time points into the future, then stop caring about the thing which is the furthest in the past and just sum over that leg, and then I get an object which has the same number of legs at the next time point, right? Because I'm always going to throw away the one which is furthest in the past and grow one which is the new one into the future. And so you can think about this as having two phases. There's a growth phase where you're keeping all of the history, and then there's a propagate phase where you're throwing away the last time point, growing the next time point. And so this gives a kind of algorithm for propagating these things, which is take my current ADT, multiply in a new layer of things which propagate me one time step into the past, do a forwards and backwards SVD sweep like you would do on any MPS representation of a quantum state, and then do the same thing over and over again. So this ends up looking very much like time-dependent DMRG, or these kind of algorithms for propagating forward spin chains or chains of quantum systems in real time. And so this means that we can use the whole toolbox which has been invented for people studying 1D quantum systems to these zero-dimensional non-Markovian quantum systems. So yeah, so this is the base tempo algorithm for propagating these kind of things. And I think in various talks from various people over the next couple of days, they will talk about different extensions to this, different ways of writing this kind of tensor network, where you can have efficiencies for calculating different things. Okay, so that's how this algorithm works, and at least our picture of what's going on with these things. What I wanted to do then was give a couple of examples of things which we've used this for. Okay, yeah, so this is the time evolving matrix product operator, which is where the tempo acronym comes from.
Can I ask?
Yeah, sure.
So looking at that picture, bottom left, there seems to be a natural sort of one-dimensionality to this. Is there a way to tackle these problems with a transfer matrix kind of a scheme?
Yeah, so you can, and Gerald will probably talk about this, you can contract this way instead, and then you end up with a process tensor type representation of this, and this is exactly that kind of idea.
The other question is that here you haven't mentioned what the bath is, so the bath can be zero temperature, finite temperature.
Yeah, so anything, yeah, so this all, it all comes in via this. So the way that you end up calculating these influence functionals has the temperature and the spectral density of the bath included in those. So that's why in this kind of, this correlation function at zero temperature is just the Fourier transform of the spectral density, but at finite temperature, you get a cost type modification to that, which takes into that into account. Okay, perfect. So yeah, so I'm going to talk about a couple of examples that we have for ways in which we've used this kind of method to simulate open quantum systems. So the first thing, and the first thing that you probably do with any of these kind of methods, is to look at the ohmic spin boson model. So this is a model where I have a system which is just a two-state system, which has a Hamiltonian, which is a sigma x term. And then there's a coupling to an environment via the sigma z of that two-state system, and a spectral density, which is linear in omega at low frequencies, and then has some high frequency cutoff. In this case, we've picked an exponential cutoff, but it's really the low frequency behavior of the environment which dominates the long time physics of these things. And we know from Leggett in the 80s that in the limit where, in the so-called scaling limit, where the cutoff frequency of this environment is much larger than the natural frequency of my spin system, there are three regimes for things that this model can do. So if the coupling strength, so the prefactor in front of the spectral density, is less than 0.5 in some well-chosen dimensionless set of units, then if you look at the dynamics of the SZ expectation value of this two-state system, then it has damped decaying oscillations. If the coupling is weak, there's some change in behavior where this goes to overdamped dynamics at 0.5. And so between 0.5 and approximately 1, you get overdamped, so just decay down to a steady state of 0. And then when alpha is above 1, there's a phase transition to a localized phase where the SZ never is able to decay away to 0.
Only at 0 temperature.
At 0 temperature, yes. So yes, sure. This is for this model at 0 temperature. If you have finite temperature, then this phase transition smears out into a crossover. Yes. And to do asymptotic scaling of what's going on here, so to really capture the non-Markovian behavior, because this localization phase is really a non-Markovian effect, because it has to remember what was the initial state of my system at t equals 0 to know what state it's in at long time. So this is really a non-Markovian effect. And to see the asymptotic behavior of this thing, then you really need to go to large memory lengths. You need to be able to capture the history of this kind of system for a long time. And so that's a thing which is helped a lot by having this tempo algorithm, because if I was thinking about doing this exactly, then I have this exponential scaling, and this tempo allows this to contract down to being polynomial.
So I don't quite understand what you mean that it has to remember the initial state for a long time. It has to do with non-Markovianity. I mean, if there is no environment, a quantum system will remember its initial state for a long time.
Yeah, sure.
So, I mean, maybe I just...
No, I mean, I guess it's kind of the reason that it is able to stay in this particular state is because the dynamics is suppressed by polaron formation with the environment. So it's kind of a little bit more subtle than what I said, but yeah, it's really, the environment changes what are the eigenstates of the system so much that it gets trapped in one of the potential wells described by the coupling with the environment.
I guess what I meant to ask was, does it forget the initial state at some point and then recalls it?
So if you make a finite memory cutoff, and that's what we'll come to in the next slide, then the steady state of this thing is always the SZ equals 0 state. So if you make a finite memory approximation at any point, then it decays away to the trivial state, and it never keeps this symmetry broken phase. Yeah.
Don't I quite agree with this, but I'll let you.
Okay, sure.
Sure. Just to, I mean, the way I learned the previous slide was all in imaginary time, and it's just an Ising model with lower interactions. So if the interactions are short range, you never have anything interesting.
Pretty much, yeah.
Okay.
Okay, good. So yeah, so this is then tempo simulations of this ohmic spin boson model at 0 temperature for different values of the coupling between the environment and the system. And we see exactly these kind of three regimes. So if the coupling is weak, so in the blue and the orange curves, then we have these damp decaying oscillations, which go to 0 in the long time limit. And then as you make alpha above 0.5, then you get the green curve, which is just clearly decaying away to 0. And then if you go up to even larger and larger alpha, then these things are decaying because we have this finite memory cutoff, but they decay slower and slower and slower as you make the memory length longer and longer. So for example, in this green case, which is definitely in a limit where the SZ should have decayed away to 0, then everything converges nicely as you make the memory length longer. But if you're in these higher alpha values above the phase transition, then you find that the dynamics don't quite converge as you make the memory length longer and longer. And so you have to do finite size scaling on it in those limits to find what would be the memory length to infinity limit of this set of dynamics.
Is that shown in the plot?
That
Memory length, or?
Yeah, so this is the next parts of this is exactly that. So this next plot is take each one of these values of alpha and plot and do this. So these dashed lines are just exponential fits to the long time dynamics of these things. And so plot the decay rate of that exponential fit versus 1 over k, so versus 1 over the memory length, and work out where it's going to cross the axis.
So you have some very large memory length.
Yeah.
What was it again?
We go up to 200, I think, 200 steps.
So we're able to get this with SPAT5 with about 20 steps.
Okay, I would be interested to see what's going on there. Yeah, so we had, so I guess this 0.05 is approximately 200 memory points in the so 200 states in this chain for the tempo algorithm.
What function is being fit there?
I think it's just it's either a parabola or a cubic. So it's some low order polynomial. We checked and it doesn't really matter what you do to fit here. It's just something which gives a good estimate as to what's going on as it crosses through the axis. So you can plot the same data in a different way. So this is now versus coupling to the environment and with different values for this memory length, so 100 up to 200 memory points. And you see that this is clearly moving down to a finite value for some values of alpha around here, and it's clearly scaling down to 0 as you're in the large alpha value. So this then allows us to kind of do this asymptotic scaling for each one of these points and get some estimate for where this thing really hits 0 in the thermodynamic limit and give some estimate for the phase transition. So the black line is our extracted 0 point crossing, and then there's some 1 and 2 sigma error bars on those fits, which then gives us some good estimate for what's going on in this kind of model as you go to memory length infinity. And this shows that you really need to do that kind of scaling to get what's going on here. Yeah.
Have you looked at the expectation value of sigma z, or alternatively the coherences of the state to make sure?
You mean sigma x? So this is all based on sigma z dynamics. You mean sigma x?
Yeah, I mean this on the sigma z expectation value only depends on the occupations of the density matrix.
Yeah, sure.
Have you looked at the coherences of the density matrix?
Yes, so they typically don't converge quite as nicely or as quickly, but at the values of k that we were going to here, everything in those cases was also converged. So if you're just looking for, I guess, small alpha dynamics of these things, then you will typically need a longer memory length to converge sigma x than you do to converge sigma z.
So weaker coupling is if the coupling is weak, alpha weak, it's harder to converge for the coherence?
So it's always harder to converge for the coherences, but if you're at really strong alpha, then sigma x doesn't do too much,
I see.
basically.
Sorry, just a very quick one. You've got the phase boundary. Are you sort of deep in the scaling limit here? Or...
I think omega c was about 5 in dimensionless units. I don't remember exactly, but it was. Yeah, exactly. Yeah, yeah, exactly. Yeah, so I think that was around 5.
Okay.
So it's not deep in the scaling limit, but yeah, exactly right. So the transition is at about 1.2. So yeah.
Makes sense.
Yeah.
So maybe you said it, but what limits your time? The time where you can go maximum time?
So you can keep propagating forwards in time as long as you want, because you have this fixed size object, which is just propagating forwards. But to get this, so when you're up at these high values of alpha, then it still hasn't really converged with the memory length. So the amount of time that you're keeping in the history. So it's that which really limits.
It's not the truncation.
It's not the truncation, it's the memory length. Yeah, it's the length of the chain that you keep.
Because your mass is decaying like the power law or something?
The Bath is power law at low frequency. Yeah. So the correlation function is, yeah. Okay. Any other questions on that before we move on? Excellent. So, yeah.
I was trying to think the question about sigma x. So the system is, in the absence of the bath, it'll continue to oscillate because that's just like a cat's paw, whatever.
Yeah, exactly right. I start and spin up, and it just oscillates.
And so when as z decays irretrievably eventually on the small alpha side, what I mean, it's like it thermalizes into 50-50.
Yeah, precisely.
Does that state with average as z equals 0 that still has coherent dynamics of something, or basically if you go to the steady state, is it stationary?
It's stationary, yeah.
For SX, SX,
everything ends up. There is a stationary, yeah.
There's a net term.
Exactly.
SX,
yeah.
SX would just polarize.
Precisely.
Okay.
Yeah.
All right. I understand.
Okay. Good. Right. Okay. So the other thing I wanted to talk about, I guess I have some time. Good. Okay. Perfect. So yeah, this tempo algorithm was really designed to calculate observables of system degrees of freedom. But actually, it turns out because you're linearly coupled to a harmonic environment, you can extract the dynamics of the environment from what's happening to the system. So if I just think about what is the Heisenberg equation for one of these Bath coordinates, so one of these AK operators of the environment, then in an interaction picture where I've got rid of the system Hamiltonian, that Heisenberg equation just has terms which relate to the coupling operator which comes with the system environment coupling and the free evolution of this thing under the Bath Hamiltonian. So I can formally integrate this Heisenberg equation of motion, and it tells me that the average of one of these expectation values of a environment observable is just related to some integral over an expectation value of the operator, the system operator, which coupled to the environment. So if I know the full dynamics of a system operator, then I can calculate the full dynamics of, so these first moments of a Bath operator. So by knowing integrals of these system operators, I can know what's going on with the environment degrees of freedom. And this is really method agnostic. So any method which gives me dynamics of a system degree of freedom, a system observable, can give me dynamics of Bath observables as well. This kind of idea generalizes to higher order moments, so I can calculate A dagger A or any multi-point correlation function of a Bath degree of freedom, but it's messy, so I'm just going to show you the equations for the first moment. And this is in a couple of papers by a PhD student that we had, Dominic Gribben. Yeah, okay, so you can write down these things. So if you have some method which allows me to compute time averaged expectation values of system observables, I can calculate time averaged expectation values of Bath observables. So what we wanted to do was just play with this idea and see what we could learn about the dynamics of a system which is doing something a little bit more complicated than the one which I just showed you, by looking at, as well as the system dynamics, looking at the Bath dynamics as well. And so the thing that we chose was a model which consists of a pair of spin-a-half degrees of freedom sitting in an environment. These things have a separation, which is going to be given by R. There's some tunnel coupling between them, which has a frequency capital omega associated with it. And so this kind of model has three important frequencies which come along with it. So there's this bare system frequency, capital omega. There's the frequency associated with the spectral density. So now we're going to be talking about a system which has a Lorentzian spectral density, so something where there is a particular peak in the spectrum at a particular frequency. And then there's also the frequency associated with the separation between these two things. So there are excitations which travel at the speed of sound between the first two-level system and the second two-level system. And so the frequency of that separation gives another frequency scale in the problem. So what you can do, you can take this kind of model and map it onto a single model of a single spin-a-half particle with a different spectral density. So the single excitation subspace for this kind of a system has two states. You can map those two states onto a spin boson model, which has a modified spectral density. So we have kind of this bare spectral density in light gray. And then if you're sitting exactly where all of these three frequencies match up, then what happens is basically a hole gets drilled in the spectral density at the frequency which all of these things are happening. And so you end up with a spectral density which is really very small, but it is finite at some frequencies. It's really zero at the frequency that you have kind of drilled this hole at. And so if you did a purely Markovian treatment of what's going on here, then you would just see free dynamics of the system, because the Markovian theory would tell you, all I care about is the spectral density evaluated at the frequency that my dynamics are happening, and that value is zero in all of these cases. You can also think about what happens if you're slightly detuned away from this exactly on resonance point, and then you start drilling holes in the spectral density at frequency slightly away from this 0 point, and we'll see what effects there are of that in a moment. So this model has quite complicated dynamics because there is this interplay between multiple different parts of the system which can have different frequencies. So you get beat frequencies between the detunings of these different parameters.
So what's the interaction, the system operator of the interaction Hamiltonian system?
So it ends up being basically the same as the one that we talked about before. It's just a sigma z coupling. So it's an SZ1 plus SZ2 for the two spin model. So this is what we get when we do these kind of simulations, and this is all quite complicated, so I'll talk you through this quite slowly. So on these line plots at the top of each one of these, so this is a 3x3 grid of different detunings between different system frequencies. So along this, which way around is it? Let me get this right. So this column is I have detuned the natural system frequency slightly away from the natural frequency of the environment to be below. And then this final column is I have detuned the system frequency to be slightly above the natural frequency of the environment. And then the different rows are, I have tuned the natural frequency of the tunneling between the two different sites in the problem to be either above or below the natural frequency of the environment. So we have this 3x3 set of results for different detuning conditions. So the easiest thing to understand is this picture in the center. And what these color plots are the collective environment degree of freedom. So basically the integral over all of these AK operators for the environment. And these dashed lines are the positions of my two quantum dots in a kind of one, so we're using a one-dimensional environment because that's the thing which gives rise to the biggest change in the dynamics here. So these quantum dots really end up looking like mirrors for excitations in the environment. So if all of my frequencies are tuned to be the same, then I get pretty good mirrors, and I get just bouncing backwards and forwards of excitations between the two quantum dots with a little bit of leakage out from each one of these mirrors. And so for all of the cases where the frequency associated with the separation between the two dots is the same as the frequency of the environment, then I get these pretty good mirrors. They're slightly worse if you have detuning away from the natural system frequency. But in these three cases in the middle, you see really just excitations bouncing backwards and forwards between each of the dots between these mirrors.
Could you say quickly one more time what the three frequencies are?
So the three frequencies are the bare system frequency, capital omega, the frequency where the peak in the spectral density sits, which is omega 0, and the frequency associated with the separation between the two quantum dots, which I'm calling omega r. So yeah, so this top row is omega r slightly detuned, the middle row is omega r is on resonance, and the bottom row is omega r slightly detuned below, and the columns are the same, but with the system frequency slightly detuned either side. So then if I detune the separation frequency away from resonance, then things get slightly more complicated. And if you just look at the system dynamics, then you see these quite complicated collapse and revival. So you get oscillations which get smaller and then get larger again. And you can really see that what that's because of is excitations traveling between the two dots at a different rate to the natural frequency of the two-level system coupling to itself. So you can really see in these environment pictures what's causing the quite complicated looking dynamics that you had in the system. So having access to what is going on in the environment can actually quite often tell you quite a lot about what is going on in the system, and that's actually accessible via these kind of techniques which naively you would think just give you access to system degrees of freedom. So actually you can get much more than that from these kind of things. Okay, and just to wrap up in the last few minutes, there are a variety of things which we have done with tempo to add on to it, and this is by no means a complete list, and there will be other people talking about other things. This is just a list which I threw together at some point. So there are easy things which one can do. So, for example, if you have a multi-level system, and that only couples to some of the transitions in that multi-level system, then this influence function simplifies an awful lot, and you get a much better scaling with system size. So one of the main drawbacks of this algorithm in its current state is the scaling with the number of degrees of freedom which a system has. So that, I guess in MPS type language, then that's your local Hilbert space dimension, and making that larger is a big problem because everything always scales exponentially with that. But there are some cases where if only certain transitions couple to the environment, then you don't get that exponential scaling. You only really care about the states which are coupled to the system. We can always put an arbitrary spectral density in this. There isn't any restriction on what the spectral density that you put into the problem is. It may happen that certain spectral densities require a longer memory time or require shorter time steps, etc., but there isn't, like in, say, hierarchical equations of motion, where you have to really decompose your spectral density into a sum of Lorentzians. You don't have to do that with this kind of approach. You can add Markovian dissipation or any other Markovian channel to your system degrees of freedom basically for free. So it just changes the time local part of your influence functional. And you can calculate things like multi-point correlation functions of both the system and using the techniques that I've just talked about, the environment as well, by using these kinds of things. There are also difficult things which various people have done. So Gerald may be talking later about simulating larger systems where instead of just having a matrix product state in time, you can have a matrix product state in space. So if I have, say, a chain of spin-and-a-half particles which all interact with different environments, then I can have kind of tempos which couple to each other via links in the system Hilbert space. You can calculate things like Gibbs states. So if you want to find out equilibrium properties of these strongly coupled system environment problems, then there are really neat ways that you can do that, which don't scale as badly as finding the dynamics of these things. There are also alternate contraction schemes based on process tensors, which I think some people will be talking about later on. You can do things like models of multiple emitters in a cavity, which look like mean field type descriptions, where each one of those emitters has a non-Markovian environment, and you can build up a tempo-like description where I have a mean field theory for cavity plus set of emitters, but each one of those emitters has some non-Markovian degrees of freedom. And there are papers covering all these kinds of things. And also one thing to highlight is all of this has been packaged by Gerald and others into a library, so Open Quantum Systems in Python, or Occupy, and this, I think, Gerald will agree, is looking for people to test and people to contribute. If anybody has questions on that, then talk to me or Gerald, and we can help with those kinds of things. Okay, and to summarize, I think, I've shown you this tempo algorithm, how it's constructed, how it works, how we build it up. I've shown that we can use it to calculate dynamics of small quantum systems really quite precisely, and also we can use it to find environment dynamics, and there are going to be quite a few talks on using this to do other things. Yeah, but just to thank all of the people that actually did the work on this kind of thing. Thanks very much.
We have time for just listing these two questions, so yes.
So have you tried calculating entanglement entropy?
We have not so much. So there are measures of, so you mean time separated entanglement entropy, because all of this there isn't really a system, there isn't a spatial degree of freedom in these problems. It's all a time degree of freedom.
No, I'm just asking the system-based entanglement entropy.
No, that would actually, yeah, I haven't thought about that. That is probably something quite interesting. I'm not sure how, there probably are ways of getting at that from process tensor type representation.
It's just a Von entropy of the reduced density matrix, right?
Oh,
Because
yeah,
if we start in a pure
okay,
state, then that's
indeed, yeah. So good point.
so
Yeah.
very
So,
easy.
yeah, the only way that these things end up in a mixed state is via interaction with the environment. So you get all of this just by knowing the reduced density matrix each time.
Just take one more question.
Quick question.
Yeah.
You spoke about spin boson model. What about fermioning problem, fermioning bars, so on? So is it straightforward generalization?
In principle, Yes, I think so. So
I do a
because it's
DMFT
all-
impurity solver, for example.
That is something that various people are thinking about at the moment. I don't think there is a tempo implementation with fermions that anybody has done, unless somebody can correct
Okay,
me.
discuss.
But I think it should be certainly possible.
There is